Alrighty guys, so welcome back. Today we're going to take a pretty sizable leap forward in our understanding of our robots. We're going to go through and formally introduce the parameters that define these joints, and I've already mentioned that there are 4 parameters that we need to use to define each of these joint link pairs. Yesterday we referred to them as lower link pairs, but in fact they can be in the upper chain of the link as well, so, or of the robot as well. So I'll just refer to them as joint link pairs. As you'll see, these are what are known as the DH or Denneved-Hardenberg parameters. And from this we'll be able to develop a transformation for each joint on our robot arbitrarily. Regardless of how that robot is configured, we'll be able to use these DH parameters to develop a transformation just like we have been for each and every one of those transformations. So before we get going with this, we of course have our warm-up of the day. Our goal is to go through and determine the inverse of the transformation from A to B. That is the transformation from B back to A. So spend a few minutes on that and feel free to ask questions if you need to. Keep in mind tomorrow there will not be a lecture video because we will be spending the day as a lab day working on assignment number 2. In the future, if I offer this class, I'm thinking that it's probably more appropriate as a full session class, but my guys' opinion. There's a lot of material here that we're just flying through. Do you guys agree with that?
Yeah.
Okay. Ultimately, too, I want to have linear algebra as the prereq for this. Right now, it's not on the books or anything, but you can see that having linear algebra, or at least as a code requirement for this class, is pretty important. So, how's it going so far, though? Is it okay, or is it overwhelming, or reasonable, lame, whatever?
It's challenging, but it's
Don't care now that some people are employed, so. All you're going to do is get that D- you need to get the degree and walk out.
I don't think I could do that.
Oh, I know, I'm the same way, so. Okay, so how are we going to go through and determine the inverse of this matrix?
the easiest first step is to take that cosine sine break up there, and then all your technically all that's changing is the negative sign and sine are flipping places.
Exactly, all we're doing here is, in order to find the inverse of the rotation matrix, we're just going through, since this is an orthonormal matrix, we're going to hit it with the transpose operation. We're just mirroring it across that diagonal. So in this case, we can say that the rotation matrix is just the cosine of 71 degrees, 0, positive sine of 71 degrees, 0, 1, 0, and then negative sine 71 degrees, 0, and cosine of 71 degrees. Okay? So sure enough, all we're doing is changing the sign on the sine term. Okay? And that same philosophy works on each of our transformation or our rotation matrices, doesn't it? Okay. In each case, we're just going to be changing the sign on the sine term. And then, of course, we know that our final row does not change. But what happens to our position vector?
You get, well, for the top one, you get 10 cosine of 71 minus 10 sine of 71.
Good. How did you calculate that?
Doing the multiplication thing going across, where you go 10 times cosine 71, 0 times 13, 10 times negative sine.
Very good. So what we have to do when we're calculating our new position vector, or the position vector from B back to A, is we first have to unrotate the frame and then move in the relative direction. So we're going to take the rotation matrix from B to A, I was looking at the wrong part of the board, times the position vector that got us from A to B. So in this case, we're going to go through and say that, well, our rotation matrix from B to A is just what we penciled in here. It is the cosine 71, 0, sine 71 degrees, 0, 1, 0, and then negative sine 71 degrees, 0, and cosine 71 degrees. And then we have, and I should put a big old fat 0 or a negative sign in front of that. We have a 10, 15, and 10. And when we go through, sure enough, we have a negative 10 cosine 71 plus a 0 plus, well, minus 10 sine of 71. In our second row, we have 0 plus 15 plus 10, but we have a negative sign in front of it, so negative 15. And finally, we have a negative times negative as a positive 10 sine of 71 degrees. Let's see, minus 10 cosine 71 degrees.
Isn't the first one 10 cosine of 71 then if the negatives?
Let me
it's
see,
negative.
so it would
the
be,
second one, sorry.
right, so it would be cosine, 10 times cosine 71 with a negative front, and a sign in front of it, and so on and so forth. Did I get that right then?
No, you got it.
Okay, good. So that means that our new position vector is negative 10 times cosine 71 degrees plus sine 71 degrees. I just factored out that 10 so I didn't have to write it twice. Negative 15 and 10 times sine 71 degrees minus cosine 71 degrees. And we're done. That makes sense? What's the point or purpose of finding these inverses? This takes us from the origin to the end effector. This would take us from the end effector back to the origin. So if we knew where the end effector was in space, or we had a destination in space that we wanted to position and orient that end effector at, we could use this transformation to take that position and orientation and work backwards through the chain to figure out what each of the joint configurations would need to be. Okay, and as I mentioned yesterday, that's really what we're going to be doing when we start modeling our software. We're going to be taking and looking at everything in Cartesian space from the end effector's point of view and working backwards through the chain in order to determine the joint configurations necessary to get the job done. Good? Any questions there? Ultimately, this is going to be done for us when we're starting to write our programs. We're going to have these transformations pre-packaged, and all we're going to be doing is, well, for a revolute joint, we're going to be changing the angle, and for a prismatic joint, we're going to be changing one of these parameters. Everything else will be the same, and we will actually derive those today for our mutual benefits. So. Okay, so are we good to go? All right, so now we are back to looking at the diagram that I introduced yesterday. And since my diagram was not as well drawn as what the book provided for us, I decided just to copy the diagram that they have in the book. That way we could refer directly to it. Because obviously I am in engineering because I'm not much of an artist. Let me make sure that the camera catches that. Ooh, it's kind of off center. Rotate up. Okay, so we have the diagram that the book provides us, and this represents our length that we have. You'll notice that we have our, well, the book is referring to this as our I-1 link. I referred to it as our K link yesterday. This then is the link that follows it, so either the I link as the book refers to it, or the K+1 link as I was referring to it yesterday. That notation really doesn't mean anything other than their subsequent links. Okay, just means that this is the first link, this is the second link, it's the link that follows it. Notice here that we've got some parameters. We've got this alpha, we've got this A, and I'm going to call this R. The reason for that is because alpha and A are really easy to get confused. In fact, how many of you have read the book at all? Okay. There's a typo in there that, in fact, uses alpha twice to describe these parameters. That's not good, right? I mean, the author was just typing along and hit the alpha key to represent both the angle and the displacement from the two joints. Okay. Well, for that reason, I'm going to strongly encourage you to use R instead of or A in representing this length from the joint to joint. In addition to those two physical characteristics, we also have this D parameter, which represents what? This characteristic and this characteristic are physical characteristics of the joint. Okay, this represents the twist angle on the link. Okay, and this represents the length of the link itself. Okay, but what are these D's and thetas over here? Well, the theta is pretty easy to recognize. That's our joint angle on our current joint, isn't it? So this is what we call our joint angle. And when would we be interested in manipulating that joint angle? That joint angle would be manipulated anytime we have a revolute joint. Okay? What would happen to the joint angle if this was not a revolute joint but a prismatic joint? If this was a prismatic joint instead, we would just say that the joint angle is 0. Okay? And in that case, we would have maybe something that looks like this. Line, actually, that's negative. Same here for our rotation matrix. What does that ultimately yield? What's the cosine of 0? 1. And negative sine of 0 is 0. 0, 0, 1. We are back at the identity, aren't we? Okay. So it doesn't really matter if we have in this case I have a rotation about x. It wouldn't matter at all if we modeled this with a rotation about y or z. When we plug a 0 in there, we're still going to end up with an identity matrix. Okay. So if this is a revolute joint, this is going to be the variable that we're manipulating in order to go through and model the motion of each subsequent joint in our robot. Okay? If it is a prismatic joint, that theta is going to be 0. Okay? What's this D then? So I have to say, you look so much less stressed now than like you did last couple days. So it's just like summer got brighter for some reason. So this D is going to be the variable that we're manipulating if we are dealing with a prismatic joint, okay? So this is our variable for a prismatic joint. Okay? So what is that variable going to be if we're dealing with a revolute joint? 0, okay? If we're dealing with a revolute joint, we're going to have no offset in this z-axis, and therefore the d parameter will be 0, okay? So what we see is that even though we do in fact have 4 variables that act as the parameters for our link description, our joint link description here, how many do we really have that we have to keep track of? I said it wrong again. We have 4, right? But only 3 of those are really important to us, because one of them will ultimately be 0, okay? And that just tells us specifically whether this is a revolute joint or a prismatic joint that we're manipulating. That makes sense? Okay, so this is what's known as the twist angle, or joint twist. Let me make sure I'm corresponding with the book. I'm sorry, link twist. And as I said, that is a physical characteristic. Holy cow. What's really bad is this is going on YouTube. Okay, our length of the link which is known as the link length, is a physical characteristic. Once we define these two for any particular joint link pair, they're fixed. We don't manipulate them. The only variables we're going to be manipulating is the theta, if we're dealing with a revolute joint, or the d, if we're dealing with a prismatic joint. Now, with this being said, if we look at our robot over there, what is the only type of joint that we have on that robot? Revolute. So in fact, we can, when modeling that robot over there, set this to 0 on every joint. And then we only have to define the link twist, the link length, and then our theta angle, representing our joint angle. Good? And these are what are known as our DH parameters. The DH parameters are named after the same guy that or guys that put on the board a minute ago. Benedict Hardenberg. As I mentioned yesterday, they were grad students at Stanford back in the day, and essentially they defined the alpha as the link twist, the r sub I minus 1, they labeled it as a sub I minus 1, as the length, the d sub I, which is the offset, and finally the theta sub I, which is the joint angle. So I have a video here that I'll pop up real quick, just to kind of walk through how we can go through and model these. This is included on notes, and I will provide a link in on the web page 2. Okay, so let's see, that needs to be down there, doesn't it? So let me erase the board and then I'll play this. It's a really good video. It kind of shows how to interpret these on a given joint length pair.
The Witt-Hardenberg parameters allow you to succinctly describe the motion of a series of rigid joints. This is useful for efficient calculation of forward and inverse kinematics. The process begins by defining the z-axis along the axis of rotation for revolute joints, or the axis of translation for prismatic joints. Since this is the first joint, the x-axis is a free choice. For later joints, each x-axis will point away from the previous joint. The y-axis simply completes the right-handed reference frame. Now if we add another joint, we can determine the transformation between them. As before, the z-axis points along the axis of rotation. The dh parameters will be derived from the common normal between these z-axes. The common normal is orthogonal to both vectors, and is also the shortest line between them. The new x-axis points along the common normal, and has its origin at the intersection of the new z-axis. Notice the origin is not within the physical actuator, because the dh parameters are only concerned with the motion of the links, not the physical placement of components. Using this protocol for laying out the reference frames, only 4 parameters are needed. The first of these, d, is the depth along the previous joint's z-axis, from the origin to the common normal. Theta rotates about the previous z-axis to align the x-axes.
They use slightly different notation, but
R is the length of the common normal itself. Most texts call this parameter A, which is unfortunately easy to confuse with alpha. Instead, calling it R is useful mnemonic, as this is also the radius of revolution for the new origin about the previous z. Finally, alpha rotates about the new x-axis to bring z into alignment with the axis of joint motion. Now there's one special case, when the z-axes are parallel. Because parallel lines have an infinite number of common normals, you can choose any d value you like in order to place the new origin at a convenient location, such as the center of a link or the tip of an end effector. The other parameters are the same as before. Theta rotates about z to align the x-axis with the normal, and R translates out along the normal to reach the new origin. Alpha is already known to be 0 in this case, since the z-axes must be parallel for this to apply, thus no rotation is needed. Congratulations, that's all there is to it.
so other than using a little bit of different notation, it's a really good video because it, goes through and illustrates the how the DH parameters were approximated or identified. This really has a lot of cool benefits for us because suddenly we can, when dealing with simple joints, instead of modeling each of those joints with, let's see, what was it, 12 parameters originally, we're now down to 4 parameters with 1 0 parameter for a simple joint. And given that any joint can be represented with a series of simple joints, well then we have it down into a incredibly simple model to represent each of our joints. For example, with these DH parameters, we can then go through and start to identify the different joints and how they would be characterized on our robot. And from that, we can develop our forward chain kinematics and our reverse chain or inverse kinematics for that model. That makes sense? And with this then, all we have to do in order to go through and build a computer model or a control algorithm for that matter of our robot is just perform these matrix multiplications of each of our transformation matrices in order to get the job done. So, this thing makes it feel like I have fly on my shirt, so I keep on trying to brush it off. Okay, so if we take a look at this, we can see that as we go through, I'll try to draw the, well, I still have the camera on, except for I already closed it. I'll just sketch it up here real quick. So we have something that looks like this with, let's see. I need to go through and actually draw that as extending this on down so I can represent that common normal that would exist there. And get the picture. This is our alpha I minus 1. This is our R I minus 1. And then our joint angle is going to be here. So if we go through and look at our forward kinematics, what's the first thing we're going to do as we're building the transformation for this? And I'll go ahead and put our D here as well. So if we want to go through and build a transformation for this, for these DH parameters, what we would see is that this transformation going from the I minus 1 frame to the, that's right, to the I frame would be, well, which thing would we do first? Which operation would we perform first? Really do a rotation. Let's see, what's that rotation about? This is our new x, so that's a rotation about x. So we go through and do a rotation operation about x by our alpha I minus 1 angle. That is fixed, as I've already mentioned. Then we're going to go through and perform a transformation or a translation operation along x by our R I minus 1. And then what?
And we would find theta.
Then we're going to do a rotation. What axis is theta rotating around? Remember, the z-axis always radiates through the joint. Okay, so we're going to be doing a rotation about z by theta, followed by a translation along z, d units long. Okay. Do you notice something here? If we look at this rotation about x and a translation along x, what could we probably do? The axis that we're moving along is the axis that we're rotating about. So is this rotation going to have any impact on that translation? Not at all, they're perpendicular. So we could perform these operations in any order, or in either order, I should say. So for that reason, we could go through and say that we have a rotation about x followed by a translation along it, and that's going to be the same as a translation along x times a rotation about x. What's the benefit of that? We know that when we translate and then rotate, we can package that into a homogeneous transformation. In fact, this homogeneous transformation would look something like, let's see, it's about x, so 1, 0, 0, 0 cosine of alpha I minus 1, negative sine of alpha I minus 1, 0 sine alpha I minus 1, cosine of alpha I minus 1, 0, 0, 0, and let's see, this is our x, so r I minus 1, 0, 0, 1. That is the matrix that describes the physical characteristics of our joint linked pair. That makes sense? Now, since we're only going to be interested in revolute joints, we can assume that this is just an identity. Therefore, we don't even need to consider it. Because if we have no displacement along this axis, then we can just say, well, with this being said, that just becomes a 4x4 identity and has no impact on the overall operations. So we won't even consider that because we're not going to do anything with prismatic joints in the class. So with this then if we, I'm going to have to erase and start over here on the other side of the board. If we go through and hit our physical characteristic matrix, as we might call it, by our rotation matrix about z, we can come up with a general description of the transformation for any joint from the I minus 1 link to the subsequent link. We could say this is the k to the k plus 1 link if we want. Okay, so we have 1, 0, 0, 0, 0, cosine of alpha I minus 1, sine of alpha I minus 1, 0, 0, negative sine of alpha I minus 1, cosine of alpha I minus 1, 0, and then our r I minus 1, 0, 0, 1. Now to multiply that by our rotation about z with no offset, we then have, let's see, cosine of theta I, sine of theta I, 0, 0, should be a negative there, and then a sine of theta I, cosine of theta I, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. So, we can go through and multiply these out and have a general transformation to express the I joint in terms of the I minus 1 joint. Well, the I joint link pair in terms of the I minus 1 joint link pair. Do you guys want to see me do this by hand, or can I just copy it off my paper? It's probably going to be equally successful either way because I'll always copy it incorrectly. I might as well just do it by hand. So we have 1 times cosine of theta plus 0 plus 0 plus 0. So we have cosine of theta I for our first element, and then we have first row by second column, so we have negative sine of theta I. Okay, and it, and then 0 plus 0 plus 0 plus 0, and finally 0 plus 0 plus 0 plus r I minus 1. Second row then is 0 plus, let's see, that is cosine of alpha I minus 1 times sine of theta I. Okay, and 0 and 0. And then finally, or not finally, 0 cosine times cosine. So cosine alpha I minus 1 times cosine of theta I. And 0 and 0. And then finally, second row by third column will be a negative sine alpha I minus 1 and 0 and let's see, 0, 0, 0, 0. Good. Third row then will be 0 and 0. That's not a 0, that's a sine times sine. So sine of alpha I minus 1 cosine, no, sine of theta I. And 0 and 0. Second, or third row by second column is 0 and cosine times sine. So sine of alpha I minus 1 cosine of theta I, 0 and 0. Third row by third column is cosine of alpha I minus 1, 0 for the first, fourth element, and then finally 0 for the fourth element in that row, and then finally 0, 0, 0, and 1. Now, we have the option. We're working on high-speed pinions cruising along at 2.4 gigahertz. So in theory, we could leave it at this point. But as far as efficiency, which is going to be more efficient? Multiplying out these two matrices each and every time, or typing in this matrix when we're modeling this. This is going to be a lot more efficient because you'll notice we have a lot of terms that we're multiplying by 0. If we go through and multiply these matrices individually, what we're going to do is use up a lot of unnecessary processor power. Okay? So when we go through and model this, we're going to use this as our generic definition of our transformation for the forward kinematics going from the previous joint to the subsequent joint. That makes sense? And with this then, we've got this done. We will be using this transformation anytime we're doing the forward kinematics for revolute joints in the class. Makes sense? At this point, we could write a short function in MATLAB, employ this function, and this is the same function we will use throughout the rest of the class to describe everything, the forward kinematics. Now, what about the inverse kinematics? Going from that end effector back to the base frame. That's really the more challenging problem. So, this defines the forward kinematics okay. The inverse kinematics would be the transformation that takes us from I back to I minus 1. What is that transformation going to look like? Turns out that this is an orthonormal set. Our rotation here is just occurring across two separate angles. It's occurring first across the x-axis. Is that, yes, first across the x-axis and then about the z-axis. So this is just a compound rotation operation. Still results in that same orthonormal set, okay? So what can we do when we're determining the inverse of the rotation matrix that's represented here? Same thing, we can just take the transpose to undo it, okay? So we can say that the rotation matrix associated with the inverse kinematics is equal to cosine of theta 1, negative sine of, theta I, 0. Let's see, second cosine of alpha I minus 1, sine of theta I, cosine of alpha I minus 1, cosine of theta I, and negative sine of alpha I minus 1, and then finally sine of alpha I minus 1, sine of theta I, sine of alpha I minus 1, cosine of theta I, and my rows are getting kind of out of whack here, cosine of alpha I minus 1, and then 0, 0, 0, and 1. And how are we going to determine the translation or the translation vector going backwards? Going to go through and unrotate the frame and then move in the opposite direction. And when we do so, we end up with the translation vector being r I minus 1 times cosine of theta I, r I minus 1 cosine, let me make sure, there we go, sine of theta I and 0. And this makes sense because why aren't we seeing alpha fall or have any influence on the translation? Alpha is on or about the same axis that r is moving in. Therefore, we don't expect it to have any influence on the inverse kinematics. Okay, so only thing we're doing is we're rotating about theta, therefore we have to unrotate about theta in order to move back to where we started from. Good? Okay, so with this, we have our forward kinematics represented for each joint and our inverse kinematics. Now this is kind of interesting because we could actually do something kind of clever here. We just got done saying that the transformation from the I minus 1 to the I joint is equal to, let's say, a rotation about x I minus 1, or alpha I minus 1, times a translation along x times r I minus 1. And then we have, let's see, what was the next thing? Oh, just a rotation about z of theta I. What would we expect to do if we're doing the inverse of this? We just work backwards through this system, wouldn't we? We'd go through and perform the rotation about theta I first, and then we do the translation along negative r I minus 1, and then we do the rotation about x by alpha I minus 1. And sure enough, if you're curious and have nothing going on Saturday night, you could go through and do this operation and end up with this exact same result. Okay? And you can see that all I did when going through this thought process was reverse the order of these operations. I had to introduce a negative displacement along x, but that's just because we're moving backwards. The fact is, everything else is the same. Okay? We're just performing these operations in the opposite order. That's kind of important to us because if we are going forward, we can follow a chain of events in the forward direction. If we're going backwards, we can just follow the events in the opposite direction and achieve the opposite effect. That makes sense? So, let me pull up the that actually went a lot faster than I expected. I'll show you the function that we're going to be using or developing Monday of next week and then using throughout the rest of the quarter. And that way you can see what we're actually doing here. You can see that in this case, here we go. Suppose I need to turn that on. I was not very efficient in my code. This was the first time I actually went through the process. Let's see, right there, and then so I definitely was not very efficient in my code, but this in fact does exactly what I described. Now, which direction are we going here? In fact, what we're doing is taking the rotation about x, the translation along x, the rotation about z, and translation along z. So are we calculating the forward kinematics or the inverse kinematics with this function?
Looks like forward to
In this case, we are going through and calculating the forward kinematics in this example. So with this being said then, this particular function will go through and calculate the forward kinematics. When we develop this function, and next week I'll talk about how you go through and call functions. This is just like you'd expect the function to be. You can either include it within your script and make references to it, or this can be saved as an entirely separate function, and you can call it from an external location. So what we can do here is we can go through and replace these four separate transformations with the transformation we just put together. And when we do so, we'll have a function that we can use for the next 6 weeks or next 4 weeks to get the transformations done for us. this will work in both our planar robot that we'll be working on this next week, as well as the spatial robot that we'll be developing thereafter. Good? So, any questions up until now? Okay, so since I'm kind of out of things to say, let's open that up for discussion on the homework. Have any of you, well, I know a couple of you have started the homework, but do any of you have questions on the homework?
Number 9.
Number 9?
Yeah.
So let me pull it up real quick.
I know how to do it, I just don't know how to do the multiplication process, because we just talked about it just a second ago.
Right.
And it is a little bit harder than what you were kind of doing.
Okay, so when we go through and do the multiplication, let's see if I can do this on the fly. What we end up with is the transformation from, let's see, so alt equal, I will need to zoom in again, won't I? Alrighty, so what we'll have is, let's see,
We can find the position of B first.
right, okay, so if we go through and find the position of the vector in frame B, we can go through and just take the transformation from B to C, multiplied by the vector. And you probably noticed something here right away. That is, these earlier examples are a heck of a lot more complicated than the problems we're going to be doing, right?
Yeah.
Because we're going to be dealing with a lot of zeros when we're working through these operations. And the fact is that MATLAB's going to be doing the work for us. So these early examples where we're, moving around a position vector with 3 characteristics is not really too realistic. Okay, so with that then we're going to have 15 cosine of 60 degrees minus 10 sine of 60 degrees. And let's see, oops. Fudge, I messed that up, didn't I?
Yeah, because doesn't the 10 go across the top?
Yeah, so we need to do, what was it? 10, 5, 15.
Yeah.
Come on, really? Try this again. Okay, so we want to do 10, 5, 15, 1. There we go. So we end up with that.
Isn't the equation though in the book you have to multiply the position in front of the other vector if we're doing translation? Because that's what it is in the book. It's like we're trying to find the position of B. It's position of C times the translation from C, or from what B pointed at C, correct?
Okay, but you have to keep in mind that we have to keep the order proper, right?
Okay.
So if we go through here and express this as, let's see, the translation from B to C. Okay, that's equals base B, C, T times what we see is that the C's cancel out, leaving us with the position of P relative to frame B, okay? So in this case, we're going to hit the position vector with the transformation, in this case, the translation, in order to get to where we're setting. That makes sense? Then when we do so, we'll end up with
I was just confused because the problem beforehand that me and you did, we did it opposite way.
oh really?
Yeah, and it still came out with the right answer, but this would give you a different answer.
Let's see, in 0 and let me work through this real quick. And then tan sine of plus pi plus 0. I hit the parentheses key too many times.